Automatic, Addison.
There are 6 demos that come out of the box with the ROS 2 MoveIt Task Constructor demo package. However, these demos are tailored for another robotic arm. We need to tailor these for our robotic arm. In this tutorial, we will create the first demo from scratch, Alternative Path Costs. Here is what the output looks like. Alternative Path Costs showcases different ways to plan and evaluate robot arm movements. It goes through 4 different methods for moving the robotic arm from a starting position to a predefined goal position. The shortest path, the quickest movement, a path focusing on minimal end-effector or the gripper motion, and a path that minimizes movement of a specific part of the arm, like the elbow. The code you will develop in this tutorial can serve as a template for some practical real-world applications. First is precision manufacturing. You can minimize end-effector motion for delicate assembly tasks. You can optimize trajectory duration to increase production speed. You can also reduce wear on joints by minimizing overall path length. 2 is collaborative robotics. You could plan predictable movements by minimizing elbow motion, enhancing worker safety. You can adjust strategies based on the task. For example, quick movements for time-sensitive operations or smooth motions for human comfort. And then finally, we have flexible manufacturing systems. You can quickly adapt arm movements to different product specifications. You can switch between optimization strategies based on current production needs. If you followed my previous tutorial, the code should already be where it needs to be. Otherwise, open a terminal window right here and move to the ROS 2, source, my Cobot ROS 2, my Cobot MTC demos, and source folder right here. And we can see alternative path cost.cpp. Make sure that you go to my GitHub and go to the folder of the same path. Okay, I've got it actually, my repo downloaded in my downloads, cloned to my downloads folder, and I'll go to my Cobot MTC demos, and let's go to source, and here is the file. You want to make sure that's in your own folder in the workspace. Okay, and then after you do that, you need to build the code. So we're going to go to cd : ROS2 and run a colcon build. All right, and then I source, after doing that, I source my bash RC. And if you've been following me, you know why I do that. That sources the workspace as well as a ROS 2 distribution that's in the bash RC file. Okay, now let's make sure we've got our setup script. So I'm going to go to cd source, cd my Cobot ROS 2, my Cobot bring up, scripts. Okay, and make sure you've got this my Cobot 280 MTC demos. So cat my Cobot 280 MTC demos. And we can see in this file that we have different alternative arguments we can add after this bash script when we run it, so that we can flip between the different demos. So we're going to run the alternative path costs. By the way, previously I told you to get that code in there from my GitHub. Add all the CPP files at this stage, because future tutorials are going to be using things like the Cartesian CPP, fallbacks, move to, IK clearance costs, so forth. So these are the arguments that we will pass when we want to run the different demos, when we run this bash script. Okay, so make sure you have that bash script in there, folks. And by the way, I've got an alias in my bash RC. And down here, the MTC demos alias, which runs bash and runs that bash script that we just looked at. Okay, because I make it easy on myself so I don't have to type out that whole path when I run it. Now it is time to launch everything, and to do that I'm going to use my alias. I'm going to do MTC _demos and then alternative path costs. Enter. Let it load. Everything's coming up. Okay, and in the far right panel, click on one of the solutions. So I'm going to click on this one. Okay, and here is what you should see when you click on the different solutions. You see the robot arm moving. Okay, let's go through this together. So the task tree right here, which we can see in this panel, reflects the structure of our program. At the top, you'll see motion planning tasks with alternative path costs underneath. This corresponds to our main task, which is designed to explore different path planning strategies. Our task is divided into 3 main stages: start, connect, and goal. These stages represent the robot's initial position, okay, the motion it needs to perform, and its final position, set to the ready position. Now the connect stage, this is where all the magic happens. In our code, we've created an alternatives container with 4 different planning strategies. 4 different planning strategies. Okay, that's these guys right here. Now the first strategy is path length. This strategy aims to minimize the total angular displacement of all joints measured in radians. We then have trajectory duration. This strategy tries to find the quickest path, minimizing the time it would take to execute the planned motion. Then we've got EEF motion. This strategy focuses on minimizing the distance traveled by the end-effector, the robot's hand, which in our code is represented by the link 6 flange. Then we've got elbow motion, similar to the end-effector strategy, but focusing on minimizing the movement of the robot's elbow, represented by link 3 in our code. Now the green check marks right here and the numbers in the second column indicate how many successful solutions were found for each part of the task. For example, you see the 4 right here, 4 and the 4. Okay, we got the 4 here next to alternative path costs. It means our planner successfully found solutions using all 4 strategies. The rightmost column displays the planning time for each component in seconds. This column helps us understand which strategies might be more computationally intensive. As you experiment with the demo, try clicking the alternative path cost line under the task tree, all right, and then select each of the different solutions. All these 4 guys over here. You'll be able to visualize how each strategy results in different robot motions. Okay. We've got simple here though. It's pretty simple here, so you don't see different motions. But if you had more complex goal, you would see different motions here of the robotic arm. And this helps you understand the different trade-offs, you know, between the different strategies. Path length, speed, movement of specific parts of the robot. Now, if you want to actually execute a particular solution, you would go over here, okay, click on whatever you want, and then click this button. See that? Execute solution. Execute solution. You click that to actually execute it, and then your robotic arm would move in Gazebo. I remember when I was first using MoveIt 2, I did not know at all how to actually execute a solution. I only knew how to plan. And you had to deep dive through the documentation, go through some tutorials and some trial and error, and eventually found this little guy over here actually does the execute solution over there. It's been in RViz for a long time, but it can be very easy to miss. That makes the actual robotic arm move, get out of the planning stage and into execution stage. Now, if you look at the terminal window, you will see the planning results. MoveIt Task Constructor uses a bidirectional planning approach. This means it can work on a problem from both ends, the start stage and the goal stage simultaneously. You can see these arrows here. Forward means when the planner finds a good partial solution from the start, it sends this information forward to help plan the next stages. Backwards means when it finds a good approach to the goal, it sends this information backwards to influence earlier stages of the plan. Now, a right arrow here represents the forward flow of results from one stage to the next. Forward flow means that a stage has successfully generated a result and is passing that result to the next stage for further processing. The left arrow indicates right here, indicates a backwards flow of results. In the MoveIt Task Constructor, okay, some stages may require feedback from later stages to adjust their own results or to optimize the plan. Therefore, the results flow backward to a previous stage for this adjustment. And a dash right here indicates no information flowed in that direction. You don't really need to know the ins and out, nitty-gritty details. This is just if you're curious. So, when a solution is found in one stage, it might impose constraints on other stages. So, propagating the solution backwards allows earlier stages to take these constraints into account, potentially leading to better overall solutions. Okay, so it's enough theory right here. If you want to understand a little bit more and go deep dive into it, just copy the whole log that you have and stick it into your favorite LLM. You can get more detailed output, but that's pretty much what you need to know, that information is passed forward and backwards. So planning isn't always just linear in a linear fashion from the start to the goal. Okay, now let's do a detailed code walkthrough. I'm going to open this up. Let's go to ROS2 source, my Cobot ROS2, my Cobot MTC demos, and source. Open alternative path costs. And here we go. So we've got the file header with the includes. This code begins with a comprehensive comment block explaining the file's purpose. So demonstrating various path planning strategies using the MoveIt Task Constructor. Okay, we outline the functionality. And we're creating multiple planning alternatives and evaluating them based on different cost terms like path length and trajectory duration. And the file includes all the necessary headers for ROS2 and MoveIt, and the Task Constructor library, setting up the foundation for our robot motion planning task. Then we've got the main function here. The main function serves as the entry point and primary workflow of the program. It orchestrates the setup of the ROS2 environment, task creation, and implementation of planning strategies. We've got the ROS2 initialization. So the code initializes ROS2, creating a computational environment for robot control. Okay, we set up a node named alternative path cost demo on this line. This node acts as a communication endpoint within the ROS2 system. We then have a separate thread right here, okay, to handle ROS2 callbacks. What is a callback? So callbacks are functions that are automatically called in response to specific events or messages in the ROS2 system. Now, by running callbacks in a separate thread, the program can continue its main planning task without interruption, while still responding to incoming messages or events. This approach enhances the system's ability to multitask. Here's where we create the tasks. We've got the task constructor right there, and we name it alternative path costs. So this task will encompass all the planning stages and strategies. It then loads the robot model for our robotic arm. This step provides the task with the detailed information about the robot's physical structure, joint limits, and other characteristics necessary for accurate motion planning. We've got our planning scene set up down here on line 66. Now, a planning scene is created based on the loaded robot model. This virtual environment represents the space in which the robot operates and where motion planning will occur. The robot's initial state within this scene is set to default values with the arm group specifically positioned in a predefined home position. This setup ensures a consistent starting point for all planning attempts. Down here on line 76, we've got the initial state creation. So we've got an initial state called start as a fixed state stage. It's a tongue twister, fixed state stage. And this stage is added to the task and represents the starting configuration of the robot. It serves as a key reference point from which all motion plans will begin. Then we've got the pipeline planner creation. This code creates a pipeline planner, a planning tool that interfaces with MoveIt's planning pipeline. And this planner can use multiple planning algorithms and post-processing steps. Includes features like planner caching for efficiency, customizable planning parameters, and options for displaying motion plans and publishing planning requests. And you can see I've got detailed comments to walk you through everything step by step. Make it very clear for you what's going on so that when you have your own robotics project, you'll be able to mix and match and adapt this and use this as a template for your own work. So that's it for this tutorial. Congratulations on getting your feet wet with a real application using the MoveIt Task Constructor. Stay tuned for more projects, and as always, keep building.